Let's continue to 2.3, which is on the precise definition of limit. And so go ahead and draw this graph. We basically want to define rigorously what we mean by that limit of f of x equals L as x approaches A. So we want to define that more carefully, basically. And hold on a second. Just I want to do the arrow there. Okay, so then draw on this graph, put in your coordinate system x, y. Usually I like to label those. We'll go and label those x, and you can put y or f of x right here. Just being consistent. So what we have then is this concept. We want to approach A. So this is an open interval, right? So this parentheses, so it's open. And it's like we're approaching A from either side. It can be from either side. So you're going in like this from either side. Okay, so as you get close to, so this is what we said in the previous sections, basically. So what we said was, as we want to be as close to L as desired by getting close enough to A. So the real issue then is, what do we mean by close, essentially? So when we say close, that's not well defined mathematically, right? I mean, that's the concept, is that getting closer and closer like this to A, let me zoom in a little bit, like that, implies we get closer and closer to L. So what we use is this concept of an arbitrary small positive number. And so we're going to use the delta epsilon, and it's stated in a certain way, certain logic, basically. So what we'll do, and this I'll define here briefly in a second, we want epsilon to be any number. So we say epsilon greater than 0. So a small positive number is what it's implied to be. And that could be anything. So what you end up getting is this interval of L plus epsilon. That's what that line is right here. This line is L plus the epsilon. And then the bottom one would then be, of course, L minus epsilon. So that's an interval. So as we get closer and closer to A, this has to happen. And so since epsilon is any number, it guarantees that closeness. Okay, so the next one is the delta. The other interval will be A plus delta and A minus delta. And you can substitute an x naught there if you wanted to. It doesn't matter. So sometimes you'll see x naught. So that's what we want to do in the logic. And when you do this, it's definitely next level stuff. So it's not gonna necessarily make sense right away. So you need to read it again and again and again, and go over it again and again and again. All right. So what do we mean by close is really the question, and so that's what this defines. So here's the precise definition of limit, and it won't be stated exactly like the book. But it means the same thing, of course. So we want to first let a function f be defined on an open interval containing A except possibly at A itself. So the function value doesn't have to be the same. So you say except possibly at A itself. So it does not, so the function does not have to be defined at A. So f of A does not necessarily exist. Okay, but it may exist, but doesn't have to. Okay, and let L be a real number. So L is defined, basically, the limiting value is defined here. Okay, so then the limit of f of x as x approaches A equals L means that for every epsilon greater than 0, there exists a delta greater than 0 such that 0 less than absolute value of x minus A less than delta implies absolute value of f of x minus L is less than epsilon. So this is the arbitrary epsilon. Then what we want to find is the existence of this delta, where, see, this absolute value of x minus A less than delta, that's the distance between A and A plus delta. So when this distance is small enough, so the small enough or close enough has to do with the existence of delta given any epsilon. So given any epsilon, there exists a delta such that this statement's true. So this is what we mean by close. So this is the closeness that we wanted to talk about. Close meaning that the difference between the limit value and the function value is as close as you ever want to get. 0.00000001, or just add as many zeros as you want and say 1. That's that tiny number. So it continues to get closer and closer and closer as you get closer to A. All right, so, and remember that doesn't always happen, right? I mean, if you looked at the sign of 1 over x, it's sat there and, like this and then like that. So right around there, it doesn't get close to a number right at 0. Okay, so then from there, we want to do proofs of definitions, or use the definition of limit to prove limits. So before, we were just kind of taking limits just because, but now we want to actually use it to prove limits. All right, so here we go. So use the definition of limit to prove, okay, 1. So these are two important things, or main things you have to do. 1, always let, you always have to say or let, so always let epsilon be greater than 0 be arbitrary. So arbitrary means it could be anything. You're not saying it has to be 0.01 or anything. You're just saying it can be anything, any number. Normally, you are assuming that it's going to be a small arbitrary number, but that's not needed. Then 2, this is the tough part, really. Where'd it go? Okay. So the tough part is to find a delta greater than 0 such that, and then that statement is true, 0 less than absolute value of x minus a less than delta implies absolute value of f of x minus L is less than epsilon. So it's this implication that's the tough part. So finding this implication here, that's what takes some work. How does that work? Like, what are you doing? And frankly, I'll show you some different levels of ones, but I only ask you to do on the homework a linear case, and also these questions is the few times I am going to want you to do this as I do it in class, or in class, as I do it on these videos, for many reasons, but for now, just you need to do it this way. So I'm going to put a note right here, must be done this way. I don't always do that in class, but in this case I am. Okay, so prove, this is what it'll say, prove by definition of limit, the limit of 3x minus 5 as x approaches 4 equals 7. First thing you want to do is, when you see these questions, is see if it is true. Like, does it actually equal 7? So let's just go to the side here. So we know this one, you can just plug it in. 4 times 12 minus 5. I said 4 times 12. 3 times 4 minus 5 is 12 minus 5. Okay, which is 7. Okay, so it does work, but how do you prove it using the definition? So this is how you do it. So we first, I want to move this down, actually. Okay, we'll move this example down. Well, let's keep going. All right, so what you say is, you say proof. And you do always need to write 1 first. You need to say, let epsilon be greater than 0. So just saying epsilon is greater than 0, period, without, you don't say anything else. That implies, because epsilon is anything, it's not representing any particular number, so it is arbitrary. So you must say that, or points will be taken off. Okay, so then what you do is you do your research. You try to figure out, so basically you work backwards. So we're going to write this down up here in the corner, right? And see what that is. So this in, so you say, so this is, so you're in Calc 1 now. So this is called research. This used to be scratch work, but now we're going to call it research, okay? So you say research. So this isn't part of your proof. So I like to do research, and then I can box it real nicely with this system here. But I'll say research. So then this is, let me show you what I mean. So I'm going to just box this thing and do my research in here. See if it makes a box. Nope, try that again. It did, but I want to move it down more. Okay, I have plenty of room to work with in there. You could do that afterwards, or just, put it off to the side, but this is what we want to do. So we want to show, so this is some explanation as well. You wouldn't have to say all this stuff, but we want to show that given any epsilon greater than 0, there exists a delta greater than 0 such that absolute value, and put in a 0 actually, 0 less than absolute value of x minus 4 less than delta implies absolute value, we'll now put in the function. So this is the function value right here. This is your f of x. So f of x is 3x minus 5. And then you say minus 7. Minus 7, that's your L, is less than delta. So that's the implication you want to state. So it's finding that delta that works. So you basically, what you do then is you manipulate this and try to see if you can find x minus 4. So let's see what happens. So start back over here, and I write 3x minus 5 minus 7 equal to 3x minus 12 in absolute values. Factor out the 3, so you get x minus 4. Don't need the absolute values around the 3, it's already positive. And then do you see right here, that is something you can control. That's your delta. So make that your delta. So this whole thing is less than 3 delta, because we already know that x minus 4 is less than delta because of this. That's what you control. So you want that to be epsilon. So what does delta have to be for that to be epsilon? So it's 3 times epsilon over 3, which is epsilon. So choose delta to equal epsilon over 3. That's what you have control over. So that's all your research. Now you got to put it in the right format. This is basically assuming your conclusion right here, right? You need to first say this and then show this implication holds. So you don't want to assume your conclusion and say that this is already less than epsilon. That's your choice of delta. So what you do in your proof is you say choose delta to equal epsilon over 3. Then, now you state it in the right order. Then if absolute value of x minus 4 is less than delta, then you state that whole thing again. Basically, everything we just did here, you're going to rewrite it. So you can, if you had an iPad like me, you could just copy that thing and just put it right there. I'll leave off a couple steps you don't really need. So I'll rewrite it. So 3x minus 5. Oh, and sometimes it's nice to show what you're doing. It's nice to say, this is your f of x minus L, which is, now you put it in, right? So now that's your f of x, which is your 3x minus 5 minus 7. And then you simplify it. Absolute value of 3x minus 12. Factor out the 3. And that's your x minus 4, which is less than 3 delta, which equals, kind of run out of room, huh? 3 times epsilon over 3. And since I can, I will move this over. Always run out of room on these things, it seems. Equals epsilon. And on my paper too, but all right, so that's the technique. This is the simplest technique that I want you to be able to do. So you're going to need to be able to do one of these linear cases. So basically it's just a linear function equals a constant. So this format you need to be able to do. So the book, this is one of those instances where the book does it differently, and I do not want you to do it like the book. So this is going to take some work. It's no getting around it. This is starting some real math at this point. Okay. I should just say more sophisticated math at this point. Couple things. Here's some logic that I need you to be aware of. So some of the logic that we're using is the implication. So if you have two propositions or sentences that are true or false, so if I say if P then Q, that's the same as P implies Q. Sometimes the books will use whenever. So if you say Q whenever P, then that's still the same implication. So those are all forms of implication. So these are all forms of implications. Okay, so we'll get more and more into logic. It's good to take a logic course where you talk about basically, let me make that into logic. Where you talk about what's equivalent. So contrapositive is equivalent. So not Q implies not P. That's a contrapositive. So study, if you haven't seen this stuff, it's a good thing to kind of, nowadays you just pull it up on the web and look at YouTube and do a little bit of research out there, what in case something's like totally foreign to you, you don't get it. Okay, we'll get more into that as we go. No need to talk more about that now. All right, so let's do another one. And I won't write as so much stuff down this time. So here's another example. And this time I'm going to continue to do examples. We'll just see how it goes. How many examples I do versus the problem sessions. So prove the limit of 2x minus 1 as x approaches 3 equals, and so what's that going to be? It's going to be 6 minus 1 is 5, right? Equals 5. Okay, so you say proof. And then first thing you want to say is let epsilon be greater than 0. That's your arbitrary statement of your epsilon. And then over here, I'm going to do some research. So your research is your scratch work, but at this level, it's called research. So we want to we're working with absolute value of x minus 5. So that's this, sorry, I said 5 meant 3. That's this. So x approaches 3 is your x minus 3. So x minus 3 less than delta, that's what you're controlling. So then your f of x minus L is what you're working with. So put that in there. 2x minus 1 minus 5. So minus 1 and then minus 5. And so that is your absolute value of 2x minus 6. And then you continue. So how would you simplify that? You can factor out the 2, right? And then do you have the x minus 3? Yeah, it's sitting right there. You factor out the 2, it's already positive. No need to put absolute values. Okay, so that's going to be, so this is what you control. This right here. All right, so we're going to make that less than delta. So that's less than 2 delta. So what are you going to choose delta to be? 1/2 epsilon. Yes. Okay, so this is your research. We're going to put this off to the side. I like to box it. If nothing else, I can because of, oops. Oh, we'll leave it like that. That's fine. Did a pentagon? 1, 2, 3, 4, 5. So I drew a pentagon, but whatever. All right, so after that, now you put it into the form of the proof. So what's your choice of delta? So you say choose delta to equal 1/2 epsilon or epsilon over 2. It doesn't matter how you write that, of course. Then you state the rest of it. So you say if absolute value of x minus 3 is less than delta, then then what? So then write the rest of it out. What's that going to be? So pause it, write the rest of it out, see what you get. So you write it, opposite value of 2x minus 1 minus 5 equal to opposite value of 2x minus 6 is equal to 2 times opposite value of x minus 3. Okay, and that's less than 2 delta, which is equal to 2 times delta. What's delta? Epsilon over 2, which is equal to epsilon. I suggest you go through this a lot. Okay, just pick any linear function, mx plus b, and try to solve it, because that's what I'm going to ask you. That and maybe a couple other cases, but that's basically it. Okay, we'll do more examples of this, and we'll do many in our problem sessions as well. And then the next video, lecture video, we will prove one of the properties. So all those properties really are, they were ahead of when it should have been given. Like really, you should be doing this definition first and then giving you properties, but it might have been a little too much right off the bat. So we're going to prove those properties, a couple more examples, and then we'll go on to one-sided limits in 2.4.